I want to go through another lecture and not record it. I have to redo the whole thing. Okay. For the benefit of our recording, we're going to jump into Chapter 8, Chemical Composition. And retake control. Here we go. There we go. All right, there's some concepts that we need to understand before we can make use of some basic information that's contained in the periodic table. What is the concept of counting by weighing? It's really not that difficult when you consider an example. Suppose you want to determine how many jelly beans are in a jar. I've seen those at various functions, club meetings, even at county fairs, state fairs. They have this big jar of jelly beans or something else. You're supposed to guess how much is in there. And the one that gets closest wins a prize. Well, in order to do that, from a quantitative standpoint, what you need to know is in this jar, you've got all these items, objects, and they appear to be similar in size and shape. And that's a good thing. But you can't dump them all out and count them. But what you are allowed to do is weigh them. So let's assume that the container doesn't weigh anything. If you weigh that thing, you'll get a mass for the total. Okay. So you know the total mass, but you want to find out how many of those things are in there. So in order to do that, you need to know an average mass for each one. If you know that, if you know the average mass, then you can take the total mass, this is your total mass, and you can convert that into numbers of beans. So many beans weigh a certain amount. Let's say we take out 10 beans and weigh them. And they weigh 30 grams. Okay. Then if the total mass is, let's just put a real number in here. If the total mass is, say, 1,300 grams, okay, then we can just use dimensional analysis to find out how many beans there are. This is our conversion factor. How much do 10 beans weigh? Or it would work just as well if you say 1 bean weighs 3 grams. Okay. So if you divide 30 into 1,300 times 10, then you find out how many beans there are in that container. Uh, 433. Of course, I rounded that off because you can't have a fraction of a bean. So that's the concept of counting by weighing. You need to know this conversion factor. That conversion factor for atoms is called molar mass. Molar mass tells us that so many atoms weighs so much. That's your conversion factor. Okay, I just did this one. There's an example where we find out how much each bean weighs, and we get an average weight for the beans. You can do it that way, or you can just weigh 10 beans. Use that. Okay, so you can look at that at your leisure. so we're just going to skip that. This example uses marbles. And it really isn't telling you anything new, it's just using a different example. If you know the marbles, all of the marbles weigh this, but 10 of the marbles weigh that, then how many marbles are in the pile? Well, you use, similarly, 39480. That's how much the total mass is, and you just need a conversion factor. This is where you are, this is where you're headed, marbles. So you need grams on the bottom and marbles on the top of your conversion factor to cancel the grams and leave you with marbles. So what we need is, how much does a certain number of marbles weigh? And we're told 10 marbles weigh 3760. So now it's just, we've done the thinking already. That's the thinking part. The rest is number crunching. Once you know that this conversion factor will cancel the grams and leave you with marbles, then you just divide that into this times 10 for marbles. And that's what it looks like mathematically. Okay, so now we're going to apply this concept to counting atoms. Why would we want to count atoms anyway? If you look at the history of chemistry, up until a certain point, the only thing that chemists knew about their reactions was mass, what goes in, what comes out. And it just did not compute, as they say. They were able to say things like, the mass that goes in is the same mass that comes out. That was a law. But they weren't able to say why these things react and give you these products. The reactants give you products. Until we were able to count the atoms. We knew the elements, we knew how many atoms of each element go in on each side, so we can tell reasonably well what comes out on the other side. But you can only do that if you can count the number of atoms. So, well, we're making a point here of how small atoms are. Right? With our standard of a gram, atoms are like 10 to the minus 24th grams in size, so they're really small. And this is the size of one atomic mass unit. Right? For reference purposes, one atomic mass unit is it's a different unit of measure, right? This equality says that is equal to that. So what can we do with equalities? We can make a conversion factor if we wanted. We could just put this one on top of that one in a quotient. That would be a conversion factor. Or flip it, be a conversion factor. One atomic mass unit is roughly the mass of one proton. Okay. So you would expect one atomic mass unit to be pretty close to hydrogen. Because hydrogen is just one proton, one electron, and electrons weigh even less than that. So an electron contributes almost nothing to the mass of an atom. One proton is basically the mass of a hydrogen atom. I'm going to hold this concept for a minute until we talk about, maybe we already have, the structure of an atom. Did we cover that already?
Yeah.
Yeah, protons, neutrons, electrons. Okay, so the value that we get here would be something, well, let's take neon since I was pointing at it. Right? So neon, remember the 4 positions around the symbol. This is the mass number, right? This is the atomic number, and then this is the number of atoms, and that's the charge. So the mass number here could be 20. But it could also be 21. That's why, I'm leading up to why this is not a whole number. This is not the mass number. This is the atomic mass, the average atomic mass for naturally occurring neon. And the way you get that fractional value is it's a weighted average of all of the isotopes. So this is an isotope with neon, that's an isotope with neon. And of course, to be neon, it has to have the same number of protons, right? But the neon isotopes will vary in the number of neutrons. Okay. So if this is the atomic number and that's the mass number, this has 10 neutrons. This one has 11 neutrons. Okay. But the naturally occurring abundance of these isotopes varies with each of the elements. It's different for each one. Some of them have almost exclusively one isotope and just a smidgen of another isotope. In those cases, the value will be very close to a whole number, like this one, arsenic. It's very close to 75, which is probably the most common isotope. It would be 33 As75. But others like chlorine are about halfway in between. So about half of its isotopes are 35s and about half of them are 36s. It gives you that middle ground. But that has to be experimentally determined, right? That's not something you can deduce. But if we know the relative abundance of each one, we can do a weighted average. It's kind of like doing your GPAs. Right? Your grade point average is a weighted average of your grades in each class. The ones that are worth 3 credit hours, your grade's heavier weighted. Like a lab that's only worth 1 credit hour carries less weight. So if you got an A in the lab, it would raise your average less than if you got an A in a 3 credit course or an A in a 4 credit course. It's that concept, weighted average. So that's what these values are. These are average atomic weights, whereas these are mass numbers. They're related, but they're not the same, because mass numbers are always whole numbers, because they represent whole numbers of things, protons, neutrons. Okay, but we need a reference, and our reference for atomic mass is carbon, and not just carbon in general, one specific isotope of carbon, carbon 12. So there's your mass number, but for this particular isotope, its atomic mass is 12. So that's 12 called nucleons. That includes protons and neutrons. Okay. So this is 12, so it has 6 protons and 6 neutrons to give you that number. So that's 12 nucleons. But we have arbitrarily set this value at also 12 atomic mass units. Okay? So it's a fine distinction there, but it's an important one because this is our basis. Everything else hinges on this carbon isotope weighing 12 atomic mass units. Then the rest of them can vary, and none of them will be whole numbers.
Why are they use that as a starting?
Carbon, well, I'll tell you, historically speaking, oxygen used to be the basis, oxygen 16. But it's very difficult to get an absolutely pure sample of oxygen 16 isotope because it's a gas. Plus, it exists in nature, it exists like that. So you would have O32, really. So they needed something that was easier to isolate because you don't want to have the whole world of chemists having to go to one place to get their samples and get things standardized. You want to be able to isolate carbon-12 easily anywhere on the planet. And carbon is, well, we're carbon-based life forms, right? All living forms are carbon-based, so carbon is readily available everywhere. You just need the equipment that allows you to separate carbon-12 from all the other isotopes. And the lion's share of carbon is 12. That's why its value, average value, is close to 12. When you include the other isotopes, carbon-13, carbon-14, they skew the value only a little bit. So most of your sample of carbon naturally occurring will be carbon-12. You just have to separate out a few 13s and 14s. Okay, does that answer your question? Sort of. Okay. Okay, so once we have our standard, then we can determine average atomic mass for any of the naturally occurring elements. So for carbon, it would be carbon-12, carbon-13, primarily. There's a little bit of 14, but it's such a small amount, it really doesn't matter. So we can essentially eliminate that one. Besides, carbon-14 is radioactive. So while you're trying to do your experiment, it's disappearing. So you might as well base it on stuff that's stable. These two isotopes are stable. Okay. So here's an example. If we know that we have a sample of carbon, and we have 431 atoms, of carbon. Okay, we want to convert that to atomic mass units. Right? So what we need is a conversion factor, because we're headed to here. We want our units to be atomic mass units, not atoms. So we need a conversion factor that will cancel the atoms. Remember, this is in the numerator, that's in the denominator, and leave us with atomic mass units. Well, one atom is really all we're going to do. So this is 12.01 per atom. Right, that's our conversion factor. So atoms cancel, and we just need 431 times 12.01. And that gives us 5,176 atomic mass units for this many atoms. Okay.
So if you start looking into atomic mass units, you're going to that coming back to the carbon, right? That's
Eventually, yeah, that's your anchor point. Right. Yeah. How about aluminum? What would we do for 75 atoms of aluminum? Just erase that one, that one. It's going to take a different conversion factor, isn't it? Because aluminum is not carbon. So we have 75 atoms of aluminum. So what's the conversion factor for aluminum? It's Got to find it on your chart, right? And you can round them off. We're looking for this number. You can round it off to 2 decimal places. That's good enough for school. I used to be able to say government work, but I don't work for the government anymore. 2698. So that's the number of atomic mass units per atom of aluminum. Exactly right. 2024. Atomic mass units for that sample of aluminum atoms. Now these are all hypotheticals, right? I don't think I would be able to locate and isolate 75 atoms of aluminum. Too small for my fingers. But the concept is, actually, this is leading to the use of a better type of conversion factor here. We'll get to it eventually. It starts with the mold. If you're going to have enough atoms that you can handle and actually determine the mass of, because most laboratories don't have the equipment required to count individual atoms. It can be done. We use a mass spectrometer to do it. But for most labs, you just have a simple balance. And you can have one that's fairly accurate, like 4 decimal places of a gram. So that'd be 1/10 of a milligram. We've got one in our lab that'll do that. I used to have one in my lab that was 6 decimal places. So it was micrograms. So it's possible to weigh very small amounts of atoms, but you still need lots of those atoms in order to register on your balance, right? Because we said 1 atomic mass unit is 10 to the minus 24, right? I don't know of any balance that'll weigh that small. I'm sure they have them, but you need lots of money just to buy one, and then lots more money just to keep it calibrated. So we need a quantity of atoms that's large enough so that we can weigh them on our balance. And that quantity is the mole. The mole is simply a number of things. For our purposes, it would be a number of atoms, a number of ions, a number of protons, a number of neutrons, something really small. That's why we want to use it in the first place. But a mole is just a number. And it happens to be that number. Things per mole. And that's the abbreviation for mole. Don't ask me why. If you write out the whole name, it's M-O-L-E. Abbreviated, it's just M-O-L. I thought that was strange. But this is not an arbitrary number. Some scientists spend their whole lives determining that number based upon our carbon-12 standard. Okay, so that standard tells them that in order to weigh 12 grams of carbon-12 is equal to 1 mole. But 12.01 grams of naturally occurring carbon, I did put a number here because it's an average of everything that's available in nature. 12 grams of any type of carbon isotope is equal to 1 mole. Okay? So this is the standard, and this value is determined based upon that mass of this isotope or that mass of this collection of isotopes, either one. And we call it Avogadro's number. Avogadro was an Italian chemist. So it's more than that, but for our purposes, he was a chemist. And his concepts regarding the relationship of mass to numbers of things is what led us to the ability to do this, to equate numbers of things with masses of things. That equivalence allows us to describe more accurately chemical reactions. Now we know numbers of atoms, numbers of molecules that go into a reaction, rather than just masses. But we need this unit of measure, mole, in order to handle our atoms and compounds. Anything smaller, well, anything approaching the size of an atom in numbers is just too small. We can't handle it. So we need this large amount. Okay. Now, before, we were saying that argon, naturally occurring argon, has an average mass for its atoms of 39.95 atomic mass units. Well, because of the choice of this number of things in a mole, that argon, 39.95, before is atomic mass units per atom, right? But because of our choice of the numbers, it's also equal to grams per mole. They're numerically equivalent. It's just that we can substitute a different unit of measure here. Grams per mole is equivalent numerically to atomic mass units per atom. Okay, this is more useful.
So the atomic mass and periodic table, they're all measured in grams. Is that right?
Yes, for our purposes, these values are grams if you have a mole of those atoms.
How do you know if you get them all?
It's kind of circular logic. You know you have a mole when you have that mass. Okay. And you know you have that mass if you have a mole. Okay. We let other chemists who do nothing else but this type of stuff all day long, you know, to tell us that these are accurate numbers. Every once in a while, the periodic table will be revised, and these numbers will change ever so slightly as they determine the mass of naturally occurring element, each of the elements, when they have a mole of them. For our purposes, they won't change because we round off to the first two decimal places. They're never going to change enough to change those two values. Like iodine is 126.90, 2 decimal places. The next revision of the table, it might come out 126.904474 instead of 73. You know, that's not going to affect us at all. But those that are working in this area need that accuracy. We don't. So now that we have a different unit of measure, it's more useful, grams per mole. That's a conversion factor. Whenever you see a quotient with one unit on top and one unit on the bottom, you have a conversion factor. We can use that conversion factor in any number of calculations that we're going to be doing. Okay, let's see. So this just emphasizes the point that if you have a mole of each one of these, they weigh a different amount. Aluminum weighs this much if you have a mole, but gold weighs this much if you have a mole of gold atoms. Why is that? Simple. You have the same number of each one, but each one of these has a higher mass. Well, gold has a higher mass than aluminum, so if you have a mole of each, the amount of gold is going to weigh more. And all you have to do is pick up a, I don't know, they don't make silverware out of aluminum anymore. What's made out of aluminum? Pan. Pick up a pan. Just imagine what a pan would weigh. If you pick up an aluminum pan, pick up a gold pan. The gold pan is going to weigh a whole lot more. And you're not likely to have one either. a pan that's that big, you know, it'd be on the order of, well, I don't know, what would that be at today's prices? Probably $100,000 or more for a gold pan to cook your eggs in. It wouldn't wear out, never wear out. Aluminum used to be more expensive than gold because it was so difficult to isolate. Aluminum is an extremely reactive element. It's always found in combination with other elements and very tightly bound. So separating aluminum and purifying it in such a way that you could make silverware out of it, it costs more than it does to find and isolate and market gold. In fact, the royalty of Europe used to show how rich and powerful they were by having their state dinners using aluminum flatware. They didn't use gold, they used aluminum. That was more impressive because everybody knew how much aluminum costs. It wasn't until we found a way to, actually through electrolysis, we separated aluminum from bauxite, which is basically aluminum oxide. But all you need to do that is just lots of free energy or cheap energy, electrical energy. That's why aluminum now is so cheap. I mean, we make foil out of it to wrap our food. Okay, so if you want to go back in time to the 1700s, 1600s, and you want to impress somebody, you want something that's really valuable, you know, just snatch up a roll of aluminum foil and carry it with you. You'll be rich in the past. Okay, so this just restates what I told you earlier. All these values are the mass of 1 mole of those atoms. That's why we call it molar mass. But I may slip and use an older term that I learned when I was coming through this torture chamber. Atomic weight. We call it atomic weight. Molar mass, same thing. So if I slip and say atomic weight, just translate in your head, molar mass. Okay, how about determine the number of copper atoms in a 63.55 gram sample of copper. We actually don't have to do that conversion because if you look, 63.55 grams is the molar mass of copper. So you have the number of atoms you have is 1 mole or 6.022 times 10 to the 23rd atoms. Kind of a trick question. Just see if you were listening and watching on previous slides. Now it's a mole. 1 mole of atoms weighs that much. That's what 1 mole of atoms represents. That's the number of atoms, 10 to the 23rd.
This is like how many atoms would you say 1?
No, you'd say 1 mole. And 1 mole is equal to that number. You have to have that many atoms to weigh this much. You can find out how much one atom weighs. Right, 63. Let's see. 1 atom of copper. Okay. And we have 6.022 times 10 to the 23rd atoms is 1 mole. So we cancel our atoms. And then we change 1 mole into grams. So that's how much 1 atom of copper will weigh. Once you do the calculations, 6355 divided by that value. Let's just do it. It's going to be a small number. Oops. That'll work. Okay, so I get 1.0, 4 places. 0.55 times 10 to the minus 22 grams. That's per atom of copper. So that's how much an atom of copper will weigh. 10 to the minus 22 grams is 1 copper atom. If we did that for gold, of course, it would be a bigger number. Each atom would weigh more. Okay. Oh, I didn't think about that. We just did the calculation, right? This is how much 1 atom would weigh. Of course, test taking technique. If you get this type of question on an exam, say, how much does 1 atom of copper weigh? 1 atom is not going to weigh that much. Or that much, or that much. Process of elimination has to be that one. 1 atom is very small weight. So you can save yourself time and trouble. Unless it actually asks you for the value, you know, like a short answer question. But if it's multiple choice, you go straight to that one. Okay, so we can use these conversion factors to find out the number of iron atoms in 4.48 moles. Of iron, number of atoms. Now, word problems. They're notorious for blowing blue smoke in your face. You have to pick out the information you need. Does it matter that it's iron? No, because we're talking about moles. And it just says how many atoms are represented by that many moles. The conversion factor is the same whether it's iron or not. 1 mole is this. Doesn't matter it's iron. It'd be the same thing for any element. The only time you need specific conversion factor for the element is if you're going to mass from moles. Then it will be different for each element. But here we're just changing numbers to numbers. And numbers to numbers, it doesn't matter what the atom is. Okay, so we have 2 times 10 to the 24th iron atoms. We could substitute anything in there. Still be the same answer. Okay. Now this one just takes a little bit more thought. A sample of 26.98 grams of aluminum has the same number of atoms as how many grams of gold? Well, it's kind of a trick question. 26.98 grams of aluminum. 26.98 grams of aluminum. Is that a mole? That's my first question. Yep. That's equal to 1 mole, right? Okay. So if you have a mole of aluminum atoms, and you have that same number of gold atoms, how much does gold weigh? 126, no, 196. 96 rounded off 97. So if you have the same number of atoms, aluminum's going to weigh this much, gold's going to weigh that much.
Wait, so how did you do that?
Well, I just said a sample of 26.98 grams of aluminum has the same number of atoms as whatever. So you say, all right, 26.98 grams of aluminum is equal to 1 mole. So if you have the same number of atoms as aluminum, you got 1 mole. So 1 mole of gold weighs this much. They're all equivalent.
Let me see.
How did you find out how much the gold?
We need to be in the habit of saying atomic mass for molar mass.
I don't care. Just understand what each one means. They're the same thing. Atomic weight is the way I learned it as molar mass. Molar mass just means how much does a mole weigh? That's molar mass. And actually, that term is accurate. Atomic weight is kind of iffy. So I try to say molar mass. I'm learning. So let's say we have a 100-gram sample of each one of these: magnesium, zinc, and silver. And you got 100 grams of each one. 0.0 grams of each one. Okay? Numbers of atoms. Which one has the greatest numbers of atoms? Molar mass, all right. Magnesium is 2431 grams per mole. Zinc is 6538 grams per mole, and silver is 10787. Okay, so if you have the same mass of each one, which one has the most atoms? The lightest one. Why? Because in order to make that much mass out of this atom, you need more of them, because each one only weighs that much. Right? So the lightest one is the one that's going to have more atoms. If they're all equivalent masses, you have to have more of each one. Now you can do it dimensional analysis wise. Just say 100 grams and do that. Then you do this for magnesium, and 24 into 100 is a certain number, but 65 divided into 100 is a lesser number, right? And 100 divided into 100 is even less than 1 mole. So the lighter the atom, if the masses are equal, the lighter the atom, the more of them you have. It's like trying to, let's see, if you filled a Colt car with helium-filled balloons, right, it's going to weigh a certain amount. How much coal would it take to weigh that amount? Maybe that much in the bottom. It takes less coal because it weighs more. All right. So those are the steps I went through to find the answer. Okay, let's say now we have silver, zinc, magnesium. Silver, zinc, magnesium. loose threads here. 107.9 grams of silver, 107.9 grams, 70 grams of zinc, and 21 grams of magnesium. We just want to put them in order from greatest to least, right? So test taking technique. You don't have to do the calculation. You can estimate. Is this equal to a mole, less than a mole, or greater than a mole? So look at silver, 107.9. That's equal to 1 mole. Okay, how about zinc? 70 grams of zinc is more than a mole, is it not? And 21 grams of magnesium is less than a mole. So now you can put them in order. This one's in the middle. And greater than that is greater than a mole, zinc. Less than that is magnesium. So there's your order. And you didn't have to even use your calculator.
Why would zinc be more than the silver?
Zinc is greater than a mole because 70 grams is greater than its molar mass. See, zinc is 6538, so 70 grams is more than a mole. All we know what to do is put them in order. Right, so I actually did the calculations there, but this is quicker. Okay. Let's see. 10 minutes till 9. We have till 9:40. That's good. So here the authors are telling you how to solve problems again. First thing you do is ask yourself, what's the question? Then you see what information you have in the problem, and only use the information that you need to answer the question. Sometimes, though, you may have to go outside the problem to get information. Like you may have to go to a periodic table to get that information to answer the question. And that's fair. Periodic table or useful information that I give you at the end of your test. It's fair to use that too. And then you want to check yourself. Does this answer make sense? Right. If you're expecting a value of 10 to the minus 24 grams and you end up with 10 to the 35th grams, something went wrong. You probably multiplied instead of divided. Okay. That can happen in calculators. Right. Garbage in, garbage out. If you punch the wrong buttons, it's just going to tell you what you asked for. Okay, molar mass, mass in grams of 1 mole of any substance, right? So that goes for elements, individual atoms, like we have molar mass here, but it also goes for compounds. And you can use the individual molar masses for the atoms in a compound to determine what's the molar mass of the compound. I think that's where we're headed. Yeah. So the molar mass of water, H2O, is just 2 hydrogens, right? So each hydrogen is 1.01 grams per mole, but you've got 2 of them. And 1 oxygen is 16, rounded off. So if you multiply that and add it to this, you get 18.02 grams per mole. Now that's how much a mole of water molecules weighs. Not individual atoms or elements, but the compound itself weighs that much per mole of this many molecules. Barium nitrate is a little more complicated, but still you follow the same procedure. we know, let's be sure. Barium nitrate, is that active? Okay, barium is an alkaline earth, so it has a 2+ charge. Nitrate is a polyatomic ion with a -1 charge. 2 times -1 is balances that one, so we know it's written correctly. We want to be sure that we can do that, still do that. Okay, so now that we have that established, now we want to what's the molar mass of that molecule? So we take barium, we've only got one barium. So we look it up, 137.33. And how many nitrogens do we have? 2. Because that subscript propagates through everything in the parentheses. So we have 2 nitrogens, which is 14.01. How many oxygens? 6. 6 oxygens at 16. Okay, I just add them all up. Oh, and the answer's there, 261.35. Okay, so that's how much a mole of that compound weighs. There are some compounds, molecules that are huge, like proteins, they're big. Some carbohydrates, like starches, cellulose in trees. What are some others? Insulin is a huge molecule. Hemoglobin is big. Right? And each one of those has a molar mass that you can assign to it. So you know if you have a certain mass of that molecule, you can find out how many of them there are. So if you knew what's the mass of hemoglobin on one erythrocyte, red blood cell, if you know the mass of how much is on that, then you can tell how many of those molecules are on one erythrocyte. And each erythrocyte has 4 iron atoms, and each iron atom can bond with 1 oxygen. So you have 4 oxygens per molecule. Then you can find out how many oxygen molecules, how many of these are on 1 red blood cell. So once you know how to do this stuff, the sky's the limit. Just need information, more input. Okay. So what good is molar mass? Well, since it is a quotient, like grams per mole, we can use it as a conversion factor. Anytime we need to convert from grams to moles or moles to grams, we can use molar mass. I don't like the way they presented this one here, because it kind of, it's accurate. I mean, it's true, but I like the linear type. This is where you are. These are the factors that get you to where you want to go. That's the way I like it. Makes more sense that way. When you start flipping things around like that, even though it's valid, it's easier to get lost. This just illustrates that you can use molar mass to do calculations. Okay, here's one. Let's go to the next step. If you're given the name of the compound, find the molar mass. Nickel 2 carbonate. Okay, nickel 2 carbonate. First of all, is that valid? Should we be saying this next to nickel? We see where nickel is located. Yeah, it's a transition metal, so it probably has more than 1 charge. So that's valid. And then carbonate is Nowhere on that chart. Right? Carbonate is polyatomic. So you got to look in your list that will be on the exam. Yeah, it's CO3 with a 2 minus. Right? And nickel, of course, it has a charge that's given to you. 2 plus. Right? So one of these combines with one of those. That's the ratio. So if we write it like this, that's nickel 2 carbonate. Now we can determine the molar mass. Until you write the compound correctly, you can't do the molar mass. You can't do it from the name. You've got to have the formula. So nickel is, I was just looking at it, 5869. There's only one of them. Carbon is 12.01 and 3 oxygens. And just add them together. You got one? You got one yet? Oh, I thought you were doing the calculation.
Oh, no, I was texting my mom back, but I couldn't.
That's all right. So add them all up and you get 118.7 grams per mole. Right? We didn't do anything to the units. Each one of these is grams per mole. So the answer will be grams per mole when you add them up.
Would you mind doing, it's kind of like similar to the one you just did exactly did because of the carbonate,
Okay?
but it's like number 1 on this one.
Okay.
And I
Yeah,
just-
give it to me.
It's,
What does it say?
it says the number of grams in 2.58 mole of sodium carbonate is, and it just has like
2.58 moles of sodium carbonate. Okay, so you have to write sodium carbonate. Here's sodium. There's carbonate. This one's an alkali metal. This one's a polyatomic. Right? So that means you need 2 of these, don't you? Okay. 2 there. So now we have our compound written. And in order to convert this to mass, was it?
yes.
You want to go to mass. Okay. So we're starting here at moles. And we want something that'll take us to mass. So we need a conversion factor that will end up with mass on top, moles on the bottom. Anytime you see a quotient with mass on one side and moles on the other, that's molar mass. It may have, you may put grams on the bottom and moles on the top, it doesn't matter. As a conversion factor, you just put the grams down here where they belong and 1 mole on top. But in this case, it's right side up. We just need to know how much does sodium carbonate weigh per mole. So we need 2 sodiums, 23 something. Yeah, 23.00. And then carbon is 12.01, and then 3 oxygens. And we just have to do the calculations. Well, and that's 46. Sodium, 12.01, and 48 for oxygens, 106.01. So this is 106.01 per mole. And then just, that's the hard part. That's the thinking part. The rest is number crunching. That's 273.51. And then you say, all right, how many of those can I keep? Well, I can keep 3 of them. So 274 grams. Because conversion factors are exact numbers, remember? They don't count. This limits the answer. Is that one of the answers? Close to it?
Yeah.
Okay.
It's too simple, isn't it?
Okay. All right. Let's see how much I've got to go. I want to pace myself so I don't run out of time. Let's see. We need to kick it up a notch. So if we have equal mole samples of each one of these, N2O, which is dinitrogen monoxide, right? Just go back to our nomenclature. Nitrogen and oxygen are both nonmetals. So you just say type 3 compound, say how many there are. Dinitrogen monoxide. Aluminum nitrate is a type 1 compound because aluminum is a metal that only has one charge, 3+. So that would be aluminum nitrate, finished, that's it. KCN is another, potassium is only one charge, a type 1 compound, but CN is a polyatomic ion, cyanide. So it's potassium cyanide, every black widow's friend. Actually, that would be too obvious. Need to use something a little more subtle. Like arsenic used to be a good one, but now we can tell. Because arsenic, even after the person's dead, arsenic still comes out in their hair, the fingernails. So you just take samples off of the corpse and determine if they were killed with arsenic. You need something.
What is arsenic? Or arsenic?
Right here.
Like, what did it do to you?
I'm not sure the mode of action in the body. I suspect that it damages maybe the liver, nervous system, definitely. Maybe the kidneys.
Also, if like that messes them, it was just screwed.
Saying what?
If they had that in their system, they would just screw like they want.
Oh yeah, you can develop a tolerance for a certain amount of arsenic. They say arsenic salts in your food adds flavor if you don't go overboard. And you can gradually build up a tolerance to it as well. It was one of the first, it was the first cure for syphilis. It was arsenic. So you would have to be under doctor's care because they would have to administer it gradually to finally kill off the spirochete that causes syphilis. Oh, I didn't even know you were gone. I'm focused. I was trying to think of the doctor's name. I think his name was Ehrlich. They called it the silver bullet. It would cure people of syphilis. But I don't think, it usually didn't kill the person. You know, you could kill the organism before you kill the person, but very often what it did was sterilize you. You beat. No more kids for you. Anyway, let's get back to the topic here. Rank these from least to most number of nitrogen atoms. So if we need to know, compare numbers of nitrogen atoms, do we need to go all the way down to the numbers of atoms? No. Mole is a measure of numbers. So we just need to know how many moles of nitrogen in each one of these. And that will tell us. If we have equal molar samples of N2O, aluminum nitrate, and potassium cyanide. So we have the same number of moles of each one. It doesn't tell us how many, so we say, okay, let's just say we have 1 mole of each, right? They're all equal. 2 moles, 3 moles, it doesn't matter. 1 mole is easier to work with, because if you have 1 mole of this, how many moles of nitrogen do you have? For this one, you have 2 moles of nitrogen, don't you? For every 1 mole of that molecule, you have 2 moles of nitrogen. For every 1 mole of this one, you have 3 moles of nitrogen, right? 3 times 1. And for every 1 mole of this one, you have 1 mole. So the least to most would be potassium cyanide, dinitrogen monoxide, and aluminum nitrate in that order. Least to most. Okay? Now, if we had different masses, or even the same mass of each one, you would have to convert to moles of each one. Then convert that number of moles to the moles of the element you're interested in. Right? And that's what this is. So you have a 100-gram sample of each one of these, order them in greatest to least number of oxygen atoms. Since we're talking about grams, you can't just go in here and say, let's see, oxygen, there's 1, 1, 2, 2. So it's a toss-up between these two. Not necessarily, because you've got grams, you don't have moles. You need to convert each one to moles of the compound. Then apply moles of atoms per compound. So for this type of problem, we need the services of Henry Ford. Set it up correctly for one, and then do the same thing for all the rest of it. So let's see, water N2O, start over here. Water N2O, C3H6O2, and CO2. Okay, you've got 100 grams of each. So here comes Ford. We got 100 grams of each one. Just do it over and over again. There are just certain minor changes that have to take place. We're going to convert to moles first, right? So we need grams on the bottom, moles on the top. And that's moles of compound. So for each mole, how much does each compound weigh? Well, we did water earlier. It's 18.02. N2O is 2 times 14.01 is 2802 plus 16.
36.02.
Is that right?
I haven't typed it in yet.
18.02, 16. 3402. Yeah, 8, 6 is 14. 3402. Okay, how about this one? That takes a little more work. 3 times 12.01. And 6 times 1.01. Okay, and then 2 oxygens, 32. That's 7409. Carbon dioxide, 12.01 for 1 carbon. And 2 oxygen is 32. Right? 4401. Okay. So now our calculation will give us moles of compound of each of the compounds. So 100 divided by 1802 is 5.55. And 100 divided by 3402 is 294. 100 divided by 7409 is 1.35. Now this is moles of each of the compounds. Okay. And 100 divided by 44.1. is 2.27. Now, for each of the compounds, how many oxygen atoms would there be? How many moles of oxygen for each one? Well, that's 1, and this is 1. This is 2, and that's 2. So this is going to be that one. This one's going to be this one. This one's going to be 2 times that, which is 2.70. And this is going to be 4.54.
How do you know what the times are? Or was it like times 2?
This is 1 oxygen per mole. This is 1 oxygen per mole. This is 2 oxygens per mole. And this is 2 oxygens per mole. We can do it this way.
Oh, no, like, that was fine the way. I just didn't understand what was going on. But then you explained it. So.
I should be consistent. So that's 1 oxygen. That's 1 oxygen. That's 2 oxygens. And this is 2 oxygens. So this is the same. This is the same. This is 2 times. This is 2 times. So now we can put them in order. So this is number 1. This is number 2. This is number 3. This is number 4. So the one with the most oxygens per molecule, either one of these, is not the one with the most per 100 grams. It's one of these. And it's only logical. Well, it is logical. Look at what percentage oxygen is of this one. It's got 2 hydrogens in there that weigh practically nothing. So it's mostly oxygen. So that makes sense. You know, we're checking ourselves. It makes sense that water has the most of any of these. Because on a percentage basis, oxygen is mostly that molecule. Okay. Now on this slide, I went all the way out to the numbers of atoms. But you don't have to do that. As long as you know the difference in moles, you're good to go. Here we go. All right. So let's see if we can answer this one before I run out of time. Wait a minute, do I want to get to something else? Yeah, okay, I'm gonna have to skip this because it'd take too much time. But I'll give you the basics. How many grams of fluorine are contained in 1 molecule of boron trifluoride? This is just conversion factor. You're going from 1 molecule of boron trifluoride. And molecule, not mole, of boron trifluoride. Okay. Then you set up your conversion factors to go from 1 molecule is how many moles. Right? So molecules is moles. Now you can find out grams. You just need the molar mass of boron trifluoride to give you the grams. Right? So once you calculate that for boron trifluoride, you can answer the question. And it's worked out there for you anyway. So you can look at it at your leisure. but I need to get onto some of these other topics before we run out of time. Percent composition. When chemists analyze compounds in the lab, the usual way that it's reported is percent by mass. All right. So if you have a compound of, say, well, it's boron trifluoride, the chemist will do an analysis and come up with some value of X percent of boron, and that's mass. Right? So what that means is that's so many grams of boron per 100 grams of sample. Okay? And do the same thing for fluorine. Now, of course, since you've only got boron and fluorine in there, your answer, the combined amounts, when you add those together, should be close to 100 grams. Okay. So this is technically how you, just the mass of the element divided by the mass of the compound times 100 is your mass percent. It's very convenient to report the analysis of a compound that way. But it doesn't tell us anything about the formula. Say you know that your compound is made up of only boron and only fluorine. Yep. Yes?
When you were doing that, if you do that calculation for the fluorine, would you do just one of the mole numbers, or would you do multiply by 3?
No, you wouldn't.
So just one.
Right. Let's say you don't know that. You just know you've gone into the lab, and all you know is you've done a qualitative analysis. So you know that your compound has boron, and fluorine, but you don't know how much. So then you do the analysis, and you come up with this percentage of boron and fluorine. Right? You don't know the compound yet.
Okay.
Right? So you just know, just know percentage.
Mm-hmm.
Okay. Then you can use that percentage to find out what the actual formula is. Okay, that's what we're going to do next. So I probably shouldn't have put boron trifluoride up there, right? Because that can confuse. You know, thinking, why didn't you multiply it by 3? I can understand 1, but the 3 part, it's a head turner. So actually what they do is, with a new compound, they only know what elements are contained, and then they do percentages. And then use that information to tell you what's the formula. Now, you can work backwards. If you already know the formula, you can calculate percentages. All you need to know is you've got a mole of your compound. So then you can say, well, for this one, Fe2O3, if we're going backwards, we know that a mole of that weighs a certain amount. Well, it's 2 times 5585 plus 3 times 16. That's how much a mole weighs. But the amount of iron in that mole is this amount. So if you ratio this to the total times 100, you get the percentage of each one. So this is just for iron, but you could do it for oxygen too. You just substitute, instead of this, you substitute that up here. And times 100. In that case, you're 69.94%.
So you got to do it for each element.
Yes.
So
Right. Question?
I was just going to say, why would you put the 2 times 55.85 grams at the bottom? It's just going to cancel out.
It doesn't cancel out because that's a plus.
Yeah, but then you're just going to divide it. Oh, yeah, I get what you're saying.
Right. It's the total mass divided into just the mass of the one element. So you have to have this in both the denominator and the numerator because it contributes to the total. Let's see. All right, we could do that same calculation for this one. This is the formula for morphine, so that's a pretty big molecule. And it's going to actually weigh this much per mole. And the contribution of carbon is here in the numerator. So that gives you a 71.6% carbon if you do that calculation. The reason I'm not dwelling on this is I want to get to something more important. How to use the percent by mass to determine the formula for your compound. That's the more important goal here. Let's see, we'll look at that one at your leisure. Empirical formulas. Okay, a couple of definitions first. That's not big enough. It won't show up on the screen. Empirical formula. The empirical formula is the simplest whole number ratio of elements in a compound. So what do I mean by that? Well, suppose we know that the compound is 6 carbons and 6 hydrogens. If you can divide these through by the same number and reduce that number, then you can generate an empirical formula. So the largest common denominator for this one is 6, right? We can divide 6 into both of them. That's the empirical formula for this compound. Same thing would happen if we use this one. This is benzene. This is acetylene. Different compounds, right? You don't have a benzene torch, you have an acetylene torch, right? But they have the same empirical formula simply because if we divide this one through by 2, we get the same value. It's the simplest whole number ratio of elements in a compound. Right, so they have the same empirical formula, but they have different molecular formulas. Being spelled. So these are the molecular formulas. These are the empirical formulas. Okay? Now, the reason we're making that distinction is you can use the percentage composition data that we just talked about to determine the empirical formula. Simple. But that information is not enough to give you the molecular formula. It's a step toward getting the molecular formula. It'd probably make more sense if I just show you. Okay. So what do these have in common? Well, they have the same empirical formula. So we're looking for a value here. I think they use an N. They use an N. I'm going to use N because they're two different values. If you find the value here that propagates through, you can convert from there to there. This value will be a 2. This value will be a 6. So first thing we want to do is find out what's this one. Then we want to find out what that one. And that will give us this. About, oh no, you have to go. I've still got a few more minutes.
Yeah.
Okay. This will be on the video. Okay. So let's use, we know the compound has carbon and hydrogen only. Right? So it's only got carbon and it's only got hydrogen. Okay, that's qualitative analysis. Then the quantitative analysis says that we have 83.65% carbon. Okay, how much hydrogen do we have? Exactly, right? So this is going to be 5, 3, 6, and 1. Yep. Okay, did I lose anybody? Okay, so this is the percentage composition for each one. Now, we want to convert that to numbers of molecules, numbers of atoms, excuse me, in the molecule. How much carbon is in there, how much hydrogen in numbers, not mass. This is mass. Percentage is, for all intents and purposes, a dimensionless number because it's parts per 100. So if it's grams per 100 grams, the grams cancel. You don't know what the units are, right? So that's why we have to say, when we say percent, what does percent mean? Is it mass per mass? Is it mass per volume? Is it volume per volume? Okay. In this case, it's mass. So if we've got this percentage of carbon in the compound, we can pick whatever mass we want. Let's just say we have 100 grams. Why would I pick 100 grams to convert this to grams? Right, because it's parts per 100. So if this many parts per 100, it's this many grams per 100 grams. So if my sample is 100 grams, I know that I have 83.65 grams of carbon and 16.35 grams of hydrogen. It doesn't have to be 100 grams. You can pick 10 grams, and it'd be 8.365. Or you can pick 1 gram. Doesn't matter. The ratio is still going to be the same, no matter how much you choose to begin with. But this is more convenient. So now that we have grams of each, we can convert to moles. Right? So for hydrogen, we have so many grams per mole. This is going to tell us how many moles of hydrogen are in that compound on a ratio basis, ratio of hydrogen to carbon. So this is 12.01. Know that. So let's see what that gives us. 8365 and 12.01. I get 6.97 moles of carbon from this amount of carbon. And then 1635 is 1619 moles of hydrogen. Okay. Now we have the ratio, but can we write the compound this way? We could, but it wouldn't make any sense because a formula needs to be whole numbers, right? So we need whole numbers down here.
Do we round up?
No, you don't round. You keep, in order to use these values, you need to have the same ratio. So in mathematical terms, that means you can multiply both by the same number or divide by the same number, and you maintain the ratio, right? So the simplest way is to take the smallest one first and divide it. This one's easy. So that's 1 mole of carbon. This one, 6.97, is 2.32 moles of hydrogen. Okay, we're getting there. Now, is there a number that we can multiply by these two? Because we've got to multiply by the same number and give us a whole number for both of them. Well, this is about 1/3. So if we multiply by 3, times 3 gives us 3 moles of carbon, and times 3 gives us 7 moles of hydrogen. So at this point, it's okay to estimate a little bit because experimental error itself is going to throw you off. It's not going to be exact. So this is very close to a third. We're safe in using 3 as our multiplier because 3 times a third is 1, right? And 3 times 6 is, 3 times 2 is 6. So 6 plus 1 is 7. That's where I got this. So now our ratio is 3 to 7, right? That's our empirical formula. Okay? That's the simplest whole number ratio of carbon to hydrogen. Okay. All right, we've done all these steps. Here we go. Empirical formula. Now, all right. It's not going to let me go to the next step. But in order to go to the next step, to molecular formula, we need to know what is the molar mass of the compound. You can calculate a molar mass for this formula, and it would be what? 3 times 12.01 and 1.01 times 7. That one wrong. There's something wrong here. There we go, 43. 43 per mole of that formula. If we had the molar mass, let's just speculate. Let's say the molar mass is 86.2. What formula, based on this ratio, would give us 86.2? That's twice this one, right? So we need twice of everything else. So our multiplier here is 2 to give us this one, C6H14. Okay, that's the basic concept. You have to have 2 pieces of information. One is the percentage composition. That gives you the empirical formula. Then, by independent means, you need to know the molar mass of the compound itself, because this only tells you the empirical weight. This tells you the molar mass of the compound. And by comparing those two, you can say, how many times do we have to multiply this one to get that one? That gives you this multiplier here. Okay? I'm sure there are examples in your review document. And I don't know if the homework has any, but I know the review document does. So it'll take you through this calculation, and then the next step is using the molar mass of the compound to find what that ratio is, 2, 3, 4, 5, whatever. Could be 1. But the example I chose made it 2. Let's see, I've got maybe 4 minutes left. Okay, so this goes through an explanation of what I just told you. Oh, there it is. If the molar mass, well, the molar mass of this formula is that. So here it is right here. I did choose right. So the molar mass independently determined for the compound is this, and the ratio of those two gives you that multiplier.
Does it matter which one's on top or bottom?
Here? Yes. Yeah. Usually, well, you put the molar mass of the compound on top and the empirical mass on the bottom. This one on the bottom and that one on the top. That way, it'll always give you 1 or greater. If you do it the other way, then it could be 1, it could be a half, it could be a third. Then how are you going to interpret that? It needs to be a whole number multiplier. Let's see. Well, that was just another example. All right, so Thursday we'll do a review, and then next Tuesday we'll have an exam on just this chapter, none other. Okay. And between now and then, if you haven't taken the exam, you need to take it.
Is that?
You're gonna take it now?
Yeah,
Huh?
I'd like to
Now?
do mine now.
You want? Let's see. Have you
I
taken?
came in.
That's right, you did. All right. Okay, so we just need to.
So,
You can have a calculator and scratch paper. Any useful information will be on the desk.
so we don't need this?
No.
Just make-
It'll be right here.
Cool.
And you can, I'll set it up so that you can rip these 2 pages off the back.
And have them easier than flipping
Yeah.
around. Okay. Yeah.
Oh, you have something for me? Huh? Oh, okay. Yes, get started whenever you're ready.
Thank you.
These are molar, these are molar masses for the compounds. Yeah, each compound, once you calculate, remember 3 times 12.01 and 6 times. Oh, right over here.
Okay.
Yeah, that's where each one of those comes from. And then if you have more than one of them, you just multiply by that multiplier.
Is this the same as that? Without the R?
Oh, well, consider,
First,
is that valid?
yeah.
You sure? Where is sodium on the periodic table? Right, it's in the first column, right? Anything in the first and second column, plus the ones with aluminum, those metals, you don't have to say what charge is. It's type 1 compound.
Doesn't matter.
Yeah. Okay, yeah, I don't do that. Turn this off. Need to be recording silent.